So on lesson 5.2, verifying trig identities, it's very, very similar to when it was lesson 5.1. In lesson 5.1, you were simplifying trig identities. But in 5.2, you're not just going to be given, in 5.1, you were given something like this, just an expression that you had to simplify. In 5.2, you're actually going to be given a whole equation. And you have to verify or show that it is an identity. What we mean by an identity is something that is true for all values of the variable. Okay, so there's a very special technique we have to do it. We're not working with a normal equation. If this was a normal equation, we'd be able to do things like, say, divide by sign. If we divide by sign, we could divide this side by sign. That's not going to work for us when we're verifying an identity. When you're verifying an identity, you have to leave one side of your equation totally alone. You have to just simplify, find the side that's the most complicated. So look at them. When we look at this side and this side, which is the most complex? Well, it's clearly this side of the equation. Work with the most complicated side of the equation and just simplify it by replacing things with things that they are equal to. You can't change the value of it, so you can't do things like divide something out. That would be totally changing it. All you can do is replace like with a like. For instance, you could replace secant of theta with 1 over cos of theta because they're equal. So that's what we're going to do. We're going to work with this side, simplify it, line up your, imagine there's a vertical line on your paper and line up your equal signs as you're going down your paper. That's how I want you to lay your work out. So work with this side a bit, simplify it a bit more, simplify it a bit more, until you have simplified it so that it is tan theta. The other side of the equation, you don't change in any way, shape or form. You just leave it as the tangent of theta. And you have finished verifying that this equation is true, that it's an identity, that it's true for all values of theta, if you end up with a statement like this, which I call identical twins, where what's on both sides of the equal sign is obviously exactly the same. If you can reach that point, then the equation you were first given is an identity. It wouldn't matter what the value of theta was, as long as theta was in the domain of tangent, this would be true for all theta. Okay, so let's have a go at doing this. See if you start on your own. I'll just see if anybody else is still waiting in the waiting room. 1, 2. Looks like you're all here. Still missing one person, but never mind. Okay, so the first thing I'm going to do on this one is I'm going to use that technique where anything that's a sine or a cosine, you leave as it is. And anything that is not sine or cosine, like secant, cosecant, tangent or cotangent, you replace them with something they are equal to that only has the word sine or cosine in it. Secant can be replaced with 1 over cos theta, they're equal. And I don't touch that side, so I'm just going to leave it blank. It's like tangent of theta is written there. So now let's multiply fractions. This is really a fraction. And remember, when you multiply fractions, you go across the top. So sine theta times 1 gives me sine theta. Then you go across the bottom. 1 times cos theta gives me cos theta. Try and line up your equal signs. And then look at this. And this is a quotient identity. We know that this is equal to the tangent of theta. So underneath it, replace it with something it is equal to. And what was on this side? The whole way down, it's tan theta, tan theta, tan theta. So it's tan theta. You want to fill tan theta in on every line, go for it. But filling those in there, you don't have to. That's optional. As long as you haven't been changing stuff, you leave it blank. So now this problem is finished because we've reached the point where I call identical twins. If you want to be super posh, you can talk a bit of Latin and put QED, which means quadrate demonstrandum in Latin, which means that which was demonstrated or something like that. It means I just proved it. It means I'm a smart person. Or you can just do something a bit more casual, give yourself a smile when you're finished. Okay. When I was at school, we actually had to use put QED at the end of every single one of these. Ugh. Okay, right. So that was one of them. Let's talk in a bit more detail about what we're doing here. We're on lesson 5.2, day 1. We'll be doing some more difficult ones of these tomorrow. And what we're doing is we're verifying trig identities. We're going to be given an equation. So it's like we've been given the answer. We've been given something complicated and what it is equal to. And we have to verify it's a trig identity by showing that it's true for all values of our variable. How do you do it? So we're going to be proving that both sides of a given equation are equal for all values. That's verifying it's a trig identity. How we're going to do it is by transforming the expression on one side of the equation until it's equal to the expression on the other side, so that we've created what I call these identical twins. So tips, you don't have to write all of these down, but some of them I'm going to want you to do a little bit of work on. Choose one side only and work with only that side. You're not allowed to change the other side in any way, shape, or form. It must stay exactly as it was given to you in the question. When you're choosing the sides, choose the side that looks the most complicated. And then you can just think, well, I'm simplifying this, I'm simplifying it. And you keep on glancing at the other side of the equation. It gives you a clue sometimes on where you're trying to get to. So the technique we've just used sometimes works, sometimes it makes the problem worse, but it's just one technique to try if you're stuck. If you have a tangent, rewrite it as sine over cos. If you have a cotangent, rewrite it as cos over sine. If you have a secant, rewrite it as 1 over cos. If you have a cosecant, rewrite it as 1 over sine. It only works, this technique, if you're changing everything into an equivalent in sine and cosine. There's no other trig function that should be in there. Okay, it only works as sines and cosines, and basically because tangent and cotangent have got those quotient identities, which are in terms of sine and cosine. And that's why it works. Okay. So what you're going to do, the only thing you're allowed to do, because you're only allowed to transform the expression by replacing something with something it's equal to. So you're basically going to be using those 11 identities we learned the other day, substituting something in place that's equal to what was there already. One of the things we're going to do, we've worked on a couple of these already, is to combine fractions over a common denominator. Here comes your first grade for today. Write that down, work out what it would be as a fraction combined over one denominator, and type your answer into chat now. Type in what the numerator, what this A plus C would turn into. Off you go. So what you have to do, your common denominator is going to be B times D. So this is only over B, so it also needs to be over D. But you're not allowed to just multiply the denominator. You have the only number you're allowed to multiply by is 1, and D over D is the number 1. Yeah, you have 4/4, you've got a whole. So that's what the first fraction will change into, and the second fraction needs the denominator B times D. So that's going to be multiplied by B over B. So this becomes AD plus CB all over BD. Now what you're doing, I know a lot of you are told that you're cross multiplying. It's not cross multiplication, but I can see why people say it is. This numerator is going to be multiplied by that denominator, A times D. This numerator is going to be multiplied by that denominator. So you are doing that, but it's not cross multiplication, because you're also multiplying those denominators together. Cross multiplication is actually something that goes over an equal sign. Okay, so that's what that is. Let's make sure. And we're going to obviously do it in a much more complicated situation. So you really need to know what you're doing so you can do it when it's complicated. Okay, the other thing we're going to do is we're going to split when you've got a numerator made out of 2 terms, I want you to get that one fraction and split it into 2. Off you go. Split it into 2 fractions and type your answer into chat. Okay, what this is both of the things in the numerator both need to be divided by b. So you've got 1 over b plus b over b, which a lot of you gave me, but that second term can be simplified. You've got 1 over b plus 1. B over b is the same value as 1. Okay? And we're going to be doing this with much more difficult things than just a letter b and numbers 1. That's why I just want to make sure you can do it when it's easy. Okay? Then when we've got fractions, you're going to have to work on multiplying, dividing, adding, subtracting fractions. That was a bit with adding and subtracting them. There's one other very valuable technique, and that's to multiply by a conjugate. Everybody write this one down. Okay, this is a very useful one. This technique is really powerful on some of the questions that look the most difficult. This is the technique that's going to make it all look a bit horrible for a minute, but then really clean up beautifully. Multiplying by a conjugate. I don't know if you remember what a conjugate is, but a conjugate it's something that's going to bring in the difference of squares. If you have a minus b, its conjugate would be a plus b. Now that's in the denominator of a fraction. And obviously, you're not allowed to just multiply the denominator by something. You're only allowed to multiply the whole fraction by 1. So you have to multiply the top by the same thing. Now, what does that equal? Distribute that 1. You'd have a plus b at the top. And at the bottom, can you see you've got difference of squares? A minus b times a plus b. That's a squared. When you FOIL it out, either memorize it turns into that, or you can FOIL it out every time. You'll always end up with a squared minus b squared. Now, what's so special about this a squared minus b squared? That is going to be it. If it isn't, then we've done something incredibly neat. 99% of the time, look at your Pythagorean identities. It's not going to be exactly one of your Pythagorean identities, but it's going to be one of your Pythagorean identities messed up a bit. Okay, just get that out of the way. Here are your Pythagorean identities. Now this here, you see here, by multiplying by the conjugate, what we've brought in, this bit down here, is a difference of squares. And if you have difference of squares in a problem, it's going to be based on one of these. Now, none of these are difference of squares. These are all sum of squares. You've got the sum of the squares on the left side of the equal sign, and you've just got one thing on the other side. You can turn all of them into difference of squares on this side by simply choosing something on the other side and subtracting it away. Like on this one, I could subtract 1 away. And I'm left with cosecant squared x minus 1 equals cot squared x. Or maybe I could have on this one subtracted this away. And now I've got, when I've got difference of squares, whenever you've got difference of squares, look for one of these that's been messed around, where one of the terms from the sum side has been subtracted to the other side. So you'll have 2 things on this side, and you'll be left with just 1 thing on this side. You'll be left with 2 things with a minus between them on that side, and just 1 on this. And it's really, really useful. You can get 2 super ugly things and simplify them all the way down, sometimes to number 1 or something like that. It's really useful, really, really helps. And sometimes the step in between is going to look like you've made a big mistake, because it will look like it's gone really complicated. Say you've started with this. If you multiply by the conjugate, your interim step is going to be that, which looks way more complicated than what you began with. It looks way more complicated, but this is probably going to turn into just one simple thing, and this might really simplify out nicely, okay? So look for it. It's a great technique. Right, let's try some of these. We'll start with this one first. So I'm going to give you 2 minutes, see where you go. Remember the rules, remember which side to work with, which side to leave on its own. If you can't do it, it's okay, but please try. Okay, so let's have a look at this one. To me, it's quite obvious. Here's the equal sign. It's much more complicated on the left than it is on the right. So when I do this problem, I'm going to do however many steps it takes, and I'm going to hopefully end up with cotangent x plus 1 on this side equal to cotangent x plus 1. That's my goal. Okay, I think the left side is more complicated. So the first thing I can do with that left, I'm going to distribute. Cosecant x times cos x. Then I've got plus cosecant x plus sine x times sine x. I'm just leaving the other side alone, so I'm just going to leave it blank. You don't have to write it out again. And this, I could try and change cosine into 1 over secant, but that's not our technique. There's no technique that says change cosines and sines. The technique is anything that's not a cosine or sine, change it. Write it with equivalent. So I'm going to get cosecant of x, and I'm going to rewrite that as 1 over sine of x. That's what it's equal to. I'll leave that cos of x alone. That cosecant I will also write as 1 over the sine of x times the sine of x. So what I've got here is 2 separate terms separated by a plus, and I've got fractions in both of them, but those weren't obviously fractions. Remember, when you're multiplying fractions, you just do top times tops. 1 times cos x is cos x, sine x times 1 gives me sine x. That's my first one. Then I've got that plus sign, and I've got 1 times sine x is sine x times 1, sine x. And then my equal sign, try and make them line up in this vertical line down the page. Okay, when I look at this one here, right, we look at that and go, oh, that's a quotient identity. That's cotangent. So this one is cotangent of x plus, and this fraction here, when you have a number divided by itself, unless it's 0, which you can't do anything with, that's undeterminable, but any number divided by itself just equals 1. So we're done. Now don't forget, on these problems, we're giving you the answer. The answer is worth nothing. Writing this final line is worth nothing at all, really. All of your grade comes from clearly writing out what you're doing here. So your work has to be very clear. Try and have something that it's been replaced by directly under it. Don't put these arrows in your work, but you're replacing something with something it's equal to. That's how to lay out your work so that somebody else can understand what you've done. Please don't put all these arrows on your work, though, and this sort of stuff. That's actually really messing it up. It's how you lay it out. Your writing doesn't have to be neat. It's how you lay it out on the sheet of paper. Leave a blank line between each line so somebody else can actually see what you're doing. Okay, that's that one. Let's try another one. Oh, this is a fun one. Which side is more difficult here? Is it 1 minus sine x, there's the equal sign. Is it 1 minus sine x? Or is it 2 minus cosecant squared divided by 1 minus sine x? I think it's obvious. This time we're going to leave this side alone. That side we're going to leave as it is. We're not going to touch it. So we're going to be going equals, 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 maybe 10 of them. I don't know. Until we end up with 1 minus sine x equals 1 minus sine x. That's going to be our goal this time. Oh, yeah, gee, got a lot of work to do. I'm going to leave you for a little while on this, seeing what you can come up with on your own. Okay, see how you go. Oh, I had a question. Sorry, before we move on. Somebody asked me on the last one, could we change cos x plus sin x into 1? Cos x plus sin x, is there an identity? This is a really good question, and it's a fault I see a lot. There's an identity that says cos squared x plus sin squared x equals 1. I don't know if you remember, but when I taught this, remember the Pythagorean theorem tells you that a squared plus b squared equals c squared. That does not mean that a plus b equals c. This is not true without the squares. It is not, it's absolutely not true that cos x plus sin x equals 1. That is not true at all. The Pythagorean identities only hold if you've got something squared, a sum of squares equal to the other side. Great question. Glad you asked that. Let's put you back on that one. So of the several ways to do it, one way would be to get this cosine squared x and replace it with something it's equal to. Now I'm going to start showing you that technique, but it's not going to be the way I actually solve it. Okay, I'll just, and the two techniques, if you actually see the other one written out, which is in my posted key online, you'll see that they actually coincide at the same point after about 2 steps. Okay, so I'm going to start showing you it that way, but I'm actually going to do it a different way. So you can write out both techniques if you like. Right, so looking at cos squared x, it's obviously squared, so I'm thinking about my Pythagorean identities. And the only one with cosine in it is the one that says sine squared x plus cos squared x equals 1. So what would cos squared x be on its own? I'd have to subtract that on this side, so I'd have to subtract it from this side, yeah? Cos squared x equals, it's the same thing as 1 minus sine squared x. So when I see that, I could write 1 minus sine squared x in its place. So writing out everything that's on the line above, but you can replace things with things they're equal to. So I'm going to replace this cos squared x with 1 minus sine squared x. Looking carefully at what you've got, this and this are not the same. They don't cancel. That would be a terrible thing to do. They're not the same because this one is squared and this one isn't. The next step in this technique would be to go on and factor this. This is difference of squares, and you could factor it. Okay, that's what you would do with using that technique, but I'm not going to do it that way this time. I'm going to bring in that technique that I said that's really useful, which is using the conjugate. So I'm going to erase that work, and I'm going to show you a totally different way of doing it. Okay, so I'm going to write down what we were given. I'm not going to replace cos squared x this time. Instead, I'm going to go, oh, look, I'm going to bring in difference of squares. 1 minus sine x has a conjugate. And I'm going to bring it in because that's going to bring in difference of squares for me. And I know that bringing in difference of squares makes things look like a big mess at first, but then it can often really clean things up. But this is a fraction. If I multiply the denominator by that, I also have to multiply the numerator by that. Now, theoretically, I could go on now and distribute that, but ooh, no, I'll wait on that. I'll hold off on that distribution for a bit. Let's just clean up what we've got in the denominator there. So don't put this on your, just looking at this, don't put that squiggly line on your work. Can you see we've got difference of squares? A minus b times a plus b. That part there is difference of squares. And remember I said if you've got difference of squares, you've probably got one of your Pythagorean identities all mixed up. So let's write out what we've got there. We've got 2 minus cos squared x. I'm not distributing leave that until I have to do anything about it. Be very careful where you draw your fraction bar line. It doesn't start under the 2. Look carefully. It starts underneath the cosine squared. That's important. And in the denominator there, I've got difference of squared. So it's my a squared, 1 squared is 1, minus my b squared. Okay. Now I said, if it wasn't there originally, if you just bring in difference of squares, look at one of your Pythagorean identities. And I hope you can look at that. And I hope it's becoming really obvious when you look at something like that. 1 minus sine squared x equals cosine squared x. If you're in the classroom, I'd ask for a show of hands and who can see that. If you need me to show you why, it's because if you have, this is the identity everyone is supposed to know. You are supposed to know this one. If I have 1, oh, that's equals 1 minus sine squared x, what I've got is I've got this and I've subtracted sine squared x from both sides. All I'm left with is this. Okay, just moving things around in those Pythagorean identities. Okay, so that's all. I'm just thinking all of this in my head. You don't actually have to write it down. You're thinking it in your head. If you need to write it down, do it on a scrap of paper. It doesn't belong on the work that you publish to show other people that you know what you're doing. Okay? Now, so this gives me 2 minus cos squared x, 1 plus sine x. Remember the fraction bar line just started there, not under the 2. And this part here, I'm in its place, I'm writing cos squared x. Okay. Now I think it should be obvious what we can do now. Just within this fraction, it's got 2 factors on the numerator and 1 factor on the denominator. You're multiplying and dividing there. Don't worry about that minus. That's nothing to do with the fraction. So I am allowed to cancel. And let's see what we've got left. We've got 2 minus 1 plus sine x. Now, I deliberately there made a mistake. If you can turn your microphone on, then do. Who can see the mistake I've made? Lots of people do this mistake. Who can see the mistake I made there? It's really simple. Can you turn your microphones on and talk? Anyone? Okay, someone's typed it incorrectly. What it is, you are subtracting all of this factor. When you're subtracting things, you've really got to think about whether parentheses need to be there. That negative needed to be distributed to both of those. So what we've got here is 2 minus 1 minus sine x. So we've reached the answer to our problem, because 2 minus 1 is 1, and we've got minus sine x. And if we look all the way back up to the top, that's what we were after. That just means ditto marks. 1 minus sine x, 1 minus sine x, 1 minus sine x, 1 minus sine x. Down here, we're going for 1 minus sine x. So we've solved it. Now that was quite a complicated problem. That's probably more difficult than something that we give you on a quiz or a test. But I'm not sure, I'm not writing them. So can't guarantee that you won't get at least one that's that difficult. When you finish, don't forget to give some indication. Do that, or be a smart ass and write QED. Okay, let's try another one. Let's not do that one. Let's do, oh. No, that one's actually easier than it looks. Can you see there? You've got I tan in a second. That one pops out quite easily. That's not the one I want to spend class time on. Let's do this one. This is a very important one. Okay? Now, when you look at this, oh, fractions, I know that gives a whole load of you little heart palpitations. This side looks easier, so a lot of you are going to be tempted to work with a fraction. And think you're probably going to turn a cotangent into cos over sine and secant into 1 over cos. You're going to end up with a fraction and a fraction. Now, if you know what you're doing working with that, that's absolutely fine. But that's where I see students make a lot of really careless errors. So I'm going to suggest on this one, we don't start by manipulating the fraction side. Let's work with the side that's cosecant x minus sine x, okay? Let's give you a couple of minutes and see how far you can get. There you go, that's the first step. You're going to change something about those. Let's give you a go. Off you go. 2 minutes. See how far you can get. So how I'm going to do this, I'm going to replace cosecant with 1 over sine. Then I've got minus sine x. One thing I could have pointed out to you at the beginning, can you see at the beginning you've got one blob on this side, and you've got a thing minus another thing 2 on this side. What you've got, and this is a pattern that's we're going to look at some difficult ones tomorrow, you're going to sort of notice these patterns. On one side, we've got this one thing, one term. On the other side, we've got one term minus another term. Okay? So we want 2 things to be able to combine together to make one thing. How can we do that? Well, if things are fractions, we know that we can combine fractions together over a common denominator, and then we do end up with one thing. It might look horrible, but that looks pretty horrible too. So it doesn't matter. The main thing is we don't want 2 terms on that side. We only want 1. So if we think of them as fractions that we're going to combine over a common denominator, that's really going to help us. So turn that one into a fraction, and our common denominator is 1 times the sine of x. So and we've got a minus in between them. Yeah, so there'll be a minus in the numerator. So this one hasn't changed. It's still got a denominator of sine x, so the numerator won't change. But the other fraction only had a denominator of 1, so that had to be multiplied by sine x. So this one has to be multiplied by sine x. So I've got 1 minus sine squared x. And look what I've got here. Do you see what that is? That's difference of squares. So go look at your Pythagorean identities. There won't be one that's written exactly like that, but that's going to be one of your Pythagorean identities messed up. It's going to be the one that says cos squared x plus sine squared x. We can write sine squared x plus cos squared x equals 1. And we have we've subtracted the sine squared x to this side. So it's gone from this side, and it's appeared on the other side as 1 minus sine squared x. And what does it equal? It equals cos squared x. So all of this I can replace with cos squared x. When you see difference of squares, go look at your Pythagorean identities, and one of them is bound to help you. So now I've got a fraction, and I had a fraction on the other side, but they don't look anything alike. Just to remind myself to give me a clue of what I'm aiming for, I'll write that there. You could write it on every line, we're just normally too lazy to. And you think, well, that really hasn't helped at all. I've got the same first letter on both of them, but no, they're not the same at all. Okay, so we need another clue what to do. We're not allowed to change this side, but we can think about it and think about, well, if I had been working with this side, what could I have changed? What do you know about cotangent x? Cotangent x is cos x divided by sine x. If I had started working with this side, that's probably what I would have done. So look, that's really similar. They're not the same. This is just cos x, that's cos squared x. So on this side, I've got something extra. But it's giving me a clue what to do. Just thinking like that is giving me a clue what to do. It's telling me, I could split cos squared x into cos times cos. Then I would have cos x over sine x with an extra cos x as well. So looking at it, I know this part here is my cotangent x. So I'm happy about this now, okay? And cos x is the reciprocal of secant x. So I'm really done. I've done it. But if you're not sure, I would be happy at that point for you to write that as the answer. But you can't see why. Let me show you what we've got here. So I'm going to do this in 2 lines, where maybe 1 line would have been sufficient. I've broken up that fraction, just sort of split. That's the same. I'm multiplying there, yeah? So this is cos x. Cos x can be written as 1 over the secant of x, the reciprocals, multiply fractions, and I've got cot x over secant x, which is what I was after. So I've made this a little longer than it needed to be. I've written out some lines that really weren't necessary. But the things that you'll learn from experience are, if you've got 1 term on one side and 2 on the other, terms are things separated by pluses and minuses, nothing to do with multiplication and division. If you've got 2 terms and you only need 1, try and get fractions that you can combine over a common denominator, and that will turn 2 things into 1 thing. Might be uglier, but then you can work with it, okay? If you have difference of squares, look for one of your Pythagorean identities that's mixed up. If you reach a point where nothing seems to match at all, and you've no idea what to do, go and look at what the goal is and think, well, what might the step before that goal be? If I was working from this side and starting here, where would I go from there? And that might help you recognize what you've got on that side, okay? Different ways of finding clues what to do. I think we're done with the lesson now. Let's have a look. That was, yeah. Okay, let me talk about homework. I'll stop recording on this. Stop.